recording. Okay, so the second half of this, the first half of the lecture, the first half of the chapter is to introduce you to the circuits called filtering circuits, right? So there's the low pass, high pass, for those of you who did watch them, and how we can just use the same ideas that we use in chapter 2 to analyze them using these generalized resistance, right? You should think about resistance as, sorry, impedance as just a generalized version of resistance, right? And one of the key things that we learned in chapter 1, right, is this thing called the voltage divider, right? Which, you have resistor 1, resistor 2, right? And then whatever the output in here, right, is that it's just the gain, which is actually R2 over R1 plus R2, right? And we're going to use that technology over and over and over again, because a lot of times we're going to end up with, instead of resistance, we end up with impedance, right? So if we're dealing with capacitors and inductors. Before we jump into that, I want to show you this section anyway, because it's in the book, and it's something that we really can't get too far into, because it's just we can do an entire class on this. How to do math using RC circuits. Okay, this section is called integrating and differentiating circuits. So it's kind of what it sounds like it does. You can actually build RC circuits. Actually does integration for you and can do differentiation for you. Okay, so in the case, so those of you who watched the lecture last time, right, in the limit where the frequency of your signal is much greater than the RC, characteristic frequency, which is just, right, 1 over RC, right? In this case, for the low pass filter, the phase difference between the input and the output goes to pi over 2, right? It switched to 90 degrees, okay? The opposite is true for high pass filter, when the frequency you're driving at is much lower than your characteristic frequency, right? Meaning you're basically have almost no signal there. What happened is that in that case, the phase goes to positive pi over 2, or positive 90 degrees. Okay, so this is all the stuff that we derived in the video lecture that most of you guys watched. Okay. The nice thing about these limits is that, well, remember that these functions are just waves, right, or combinations of waves, right? So one of the things we know that while a cosine function, right, is shifted, let's say by a phase of minus 90 degrees, right, that's the same thing as a sine function, right? A cosine function shifted by positive pi over 2 or 90 degrees, right, it's actually just negative of a sine function, right? So the cosine and sine are just shifted relative to each other by half a period. Okay, so for a low pass filter, what we can do is that, well, and these are going to be like proportionality signs, so they're going to have some factor in front of it that's not going to be exactly the same. But how the wave behavior of it is that, well, if let's say my input wave is just some amplitude times, so this should be capital V, right? The book is just being inconsistent, and has some frequency omega, right? The output for a low pass filter, right, it's going to be the same thing but shifted back by 90 degrees, right? And that means we can change this, right, into a sine function, right? Once we change it in sine functions, that, well, the input and the outputs are actually related to each other by the fact that, well, if you integrate cosine, so yeah, if you integrate cosine, you end up with a sine function, right? So essentially, when you put a low pass filter on something, you essentially are integrating the input function, right? So it's sort of a neat thing you can do with these circuits. The opposite is true for a high pass filter. We don't have to go through all the math and stuff like that. What happened is that basically you're just differentiating the function. Okay, so a high pass filter is equivalent to a differentiator, and then a low pass filter is equivalent to an integrator. Okay, So when you integrate a fast signal, meaning you have some really fast wave that you can't look at, right? Right? You want to put a low pass filter on it, and that low pass filter is actually doing integration for you. So it kind of accumulates what is the voltage or whatever amount of charge you're trying to measure, right? So it gives you a cumulative effect. That's what a integration is, right? So let's say you have here, you have some fast signal, right? And then you put a low pass filter on it, then you just kind of get this gradual change as it adds up. It's just kind of integrating this area under the graph for you. Okay. When you differentiate a signal, what's useful about that, right? When you have a signal like this, right? When you differentiate a signal, you're basically calculating the slope of that signal at every point, right? Because that's what differentiation is. Okay. So these are very useful because, right, if you set that differential to 0, you can find all these peak points, right? Because this is when the function slope is 0, right? You can also find when it's the steepest, right? You can either find the maximum or minimum of this differential, right? And then you can use that as a way to figure out where the peaks are, right? Where they are, how fast they're going up and down. And essentially, whenever you guys push the trigger, when you have that little trigger button, and it asks for edge trigger, right? That little symbol here, right? The way it does that is by differentiating the signal and see that it has a very large downward slope, and that's why it triggers on it. Okay, so all these electronics happen in real time just by using a resistor and a capacitor together. What drives even more deep is that if you want to do Fourier transform with your signal, remember that Fourier transform? I mentioned this. I told you guys, to not worry too much about the math, but just kind of think about the idea. Is that remember that any function, right, that you want can be represented by combinations of sines and cosines, right? Okay. But you have to calculate what this coefficient in front of it all the time is, right? In order to weight, the different frequencies of sines and cosines properly, right? When you want to calculate this, right, this coefficient, right, is whatever your function is times times the just a regular wave with different different frequencies depending on what this Cn is, right? This is doing a bunch of integration, right? You multiply those two signals together, you have to integrate it. How do you integrate things? Right? You put it through a low pass. Well, you put it through a RC filter. I don't want to call it a low pass anymore. Okay? So in electronics, you have these devices that you can build physically that does Fourier transform for you. Okay? And this is basically how all of our technology works, is because when the Wi-Fi signal comes from wherever the hell the router is, right? It sends that signal out, right? Let's do that in green, right? It's just voltages, high and low as a function of time, right? It's just oscillating. It's just one antenna, right? Making a voltage high and low, and it's just sending this information out, right? How do you decipher, all the different frequencies in there? You do a Fourier transform of this signal to separate out all the different frequencies, and that way each of the frequencies represent a certain little bits of information. Maybe this frequency represents, the letter A, right? This frequencies represent a letter B, or stuff like that. It's just, this is information, and all this information gets gobbled up together when you're transmitting, right? In order to decipher the frequency that's coming out, right? You need to do what's known as a Fourier transform, which basically is calculating this integral all the time extremely fast, right? Basically in real time. Okay, so unfortunately, in a one semester course, there's no way for us to deal with this. Okay, especially since a lot of you guys probably haven't heard about Fourier transform outside this class yet, right? So because a couple of you are seniors, so you had math physics all the way through already. So, but this is I just want you guys to get the concept of this, where any signal, right? This random gobble of signal that when you look at it on an oscilloscope, you can just see it in the air, right? In order to figure out what that information means, you have to separate all the little frequencies, right? The way to separate all these frequencies is to multiply that signal by a sine and cosine function and then do an integral, right? In order to do an integral, you just need an RC circuit, okay? And that's sort of an interesting thing. So there's a free article on electronicslab.com that, you know, those of you who are really interested in signal processing and how do you separate all these different frequencies and how do you analyze them, and, you know, how do you optimize for signal to noise, feel free to read this little article. I didn't read it this year. Last year I did read it, and it was really interesting how you can actually use just RC circuits and then filtering and then doing these integration. That way you can actually figure out what the information in the air is. Because you can actually do that right now with all the information that's flying through the air right now. You can measure what that is. Unfortunately, they are encoded, right? They are encrypted, right? But if you have the decryption key, you can actually just grab all that stuff out of the air, okay? And by the way, I think some of you guys might know this already from my previous class, right? The way we encrypt things is just by having like 10 numbers, you multiply them together, and then you have to, in order to decrypt it, you just have to factor that number, right? At least currently, that's how we do encryption, right? And eventually, the idea is that like a quantum computer is supposedly be able to do this in seconds versus like 20 years. The reason that your information, you know, whatever email you're sending to each other, or, you know, the credit card information that you're sending over internet, the reason that it's safe to do that right now is because in order for someone to decrypt that, it'll take them 10 years, right? Since that's the case, in 10 years from now, that your information is actually not useful, right? Because they don't care about your bank account 10 years from now. They want your bank account number now, right? And then so whenever the quantum computer comes out, that they're going to be able to do that in seconds. So then everyone can read each other's email and bank information now. And that's also the reason why a lot of companies are actually collecting data and storing it in big servers so they can use it in the future once they can decrypt it, by the way. Just to let you know, don't expect any privacy in a few years, okay? That's all. Okay, that's a little sidetrack information. Okay, but let's go back to our little simple circuit, okay? By simple, what we're going to do, instead of just dealing with RC circuit, we're going to put a little inductor in it, okay? We haven't used inductor much. If we were in the lab, I can actually pick one up and show it to you guys. They basically they look like little batteries. Okay, I think it's actually black, right? They look like this. At least the ones we have. Okay, they could look a little bit different. We haven't done much with with inductors because they're actually not as good as capacitors. Remember that the idea of an inductor is that it kind of acts opposite as a capacitor, right? Instead of a phase shift of minus pi over 2, you get a phase shift of plus pi over 2, right? And it's kind of interesting that, you know, that inductors actually is more expensive to make, okay? B, also drains power from a DC source, right? So let's say I have a little, I just connect a little battery here, right? And then I just have it go through an inductor to ground, right? Or even just connect the two ends, right? Okay, why is this a bad circuit? What's going to happen? Right. Basically, remember what the impedance of an inductor is? Or maybe not. Yeah, all of you guys derived it in class, right? What is it? J omega L, right? What's the frequency of a DC circuit? 0. So the impedance of this basically goes to 0, right? That means you basically hooked up a no resistance circuit, right? And basically what you did is just connected with this end of the battery to this end of the battery is just going to drain the battery, okay? So a inductor is not good on these situation where you just have a constant voltage, right? So you're just constantly draining power out of your system for no reason, right? Where a capacitor, right, on DC, what happens? How much current can pass through a capacitor on DC? No. I'm sorry? No current. No current, right? Because Another way to think about this is that, well, the impedance of a capacitor is 1 over j omega c, right? So therefore, if you have 0 down there, the impedance is infinite, right? So both the math and your intuition hopefully works out, right? Okay. So what we're going to do is we're going to add this little L into our RC circuit to make an RLC circuit, because the reason is that it behaves exactly opposite of an inductor, sorry, a capacitor. Okay, so this is the circuit that the book decided to use. Sometimes, if you look at it on the internet, a lot of people actually build it like this. It's going to be, its behavior is almost the same, so don't worry about the difference between the two. Okay, right? Oops, this is L. Both of these are called parallel RLC circuits. Okay. Okay. All right. So how do we analyze this thing? Okay. So the first thing we want to do is to simplify this circuit, right? Right. Just want to make sure I'm going through the math efficiently. Okay. So what I want to do is basically take this whole lump here, right, and then simplify that parallel component into one. So I want to turn this circuit into, right, one resistor and something that has, you know, impedance of LC, right? The reason I'm labeling this LC is because there's an L and a C in it, right? Right? I want to simplify it like that, okay? So what's the impedance of this LC part in parallel, okay? Parallel, okay? Right? When things are in parallel, right, that's the more complicated way to add resistance, right? And since we know impedance is the generalized version of resistance, right? So in order to add these impedance, right, we do it the more complicated way, right? So we have to know the impedance of the inductor, the impedance of the capacitor, and it's all flipped upside down, okay? All right, so let's plug these in and see what happens, right? So over here is j omega L, right? Impedance of a capacitor is 1 over j omega c, so the upside down version of the upside down is the numerator. Okay, so we actually have just j omega c here. Still all upside down. Okay, all right. In order to do a little algebra with this, we have to combine these two terms, right? So the common denominator between them is going to be j omega L. So I multiply the bottom by j. Oops, I multiplied this by I multiplied this second term. I'm going to give me more space here, right? By j omega L, the top by j omega L. Yeah. Okay, now we have a common denominator between them. Now we can squish them together. The first term is just 1. Okay, j squared is -1, right? And then this is going to give you omega squared, and then L, and then C, all of them over j omega L, right? Right, there's still this -1 here. So with that -1, now that we have a common denominator, we can flip the thing upside down. Okay, this is j omega L, 1 for minus omega squared times LC. Okay, now at this point, what I'm going to do is I'm going to do a little Hessian thing where I'm going to declare this thing to be, I'm going to call something called omega LC. I'm going to make that equal to 1 over the square root of LC. Okay, that means, right, omega LC squared is going to be equal to L over C, right? Right. So over here we have the numerator version of it. So that means if I plug this in here, I'm going to get the denominator of it. Okay. Okay. So I'm going to plug that over into here. 1 minus omega squared over omega LC squared, right? Okay. And this is known as the resonant frequency. Resonance frequency of the LC circuit. Okay. That's the frequency it's going to resonate at. We're going to see that in a second here. Okay. All right. Cool. Okay. So that's that just started this, right? That just got us to this part, right? Now we have this voltage divider. Well, now we have this R, and then another thing with the impedance ZLC with this complicated equation, right? Right? Instead of doing this whole analysis with Kirchhoff's law and Ohm's law and all that stuff, we know what the gain of this circuit is, right? If this is V in and this is V out, what is V out going to be equal to in relative to V in? Right? Okay. Okay. So this is a complex number, right? Eventually what will happen is you have to just get the real part of that. Actually, you need to take the magnitude of that. But, right, to calculate what the gain is, right, we just need to take the ratio of the impedance of the second component over the sum of these two, right? That's the same thing as up here, right? I think I actually wrote that up here somewhere. Remember this, right? That's the gain, right? That's the same thing, right? You're gonna use this. That's why we spend an entire like half an hour on this circuit, right? And you built like 5 of them in the lab, right? Because you're gonna use this over and over again. Because what's happening is that these are resistors for now, right? But they generalize to being impedances, right? So you can actually do this same technique all the time. Whenever you're taking the output between two devices, you want to figure out what's the output relative to the input. It's always going to be R2 over R1 plus R2, right? Okay, that's a very neat thing to do. Okay, all right, so we want to figure out what we want to calculate right now. Yeah, let's calculate the gain, right? The gain, right, that's going to be a function of the frequency, right? It's whatever the impedance of the LC thing is plus R over the impedance of the LC, right? Okay, right, that's our R2 over R1 plus R2, right? All right, so now we get to plug in all this stuff with these complex numbers in it, right? 1 over J, 1 plus omega square, omega LC square, right? All over R plus J omega L, 1 plus omega square over omega LC square, all right? All right, bunch of complex number, numerator, a bunch of crap everywhere. Okay. All right, let's see how we're going to simplify this. Okay. So let's multiply the top and bottom by omega square. Sorry, 1 minus omega square 1 over omega LC square. Because what will happen is that this will cancel this out, right? If I did this to the numerator, I have to do the same thing to the denominator, just to be fair, right? Or actually just doing math, right? All right, nice thing about it is that when you multiply this to the second term, they cancels out with this also, right? That's kind of cool. But we do have to multiply out the first term completely. Okay. So what's going to happen here is that this cancel out, so we don't need that anymore. Okay. This multiply with R, so it's R times 1 minus omega square, omega LC square, right? This second term, right, when you multiply this to the second term, it cancels out this one, so this is actually just J omega L, right? Whew. All right, so this is the complex gain of your circuit. You can probably simplify this a little bit more to just get the J in one spot, because usually having the J in one spot is nice because that tells you, oh, which part is imaginary, which part is real, right? I'm not going to do that because we're going to do a little bit more math with this. And remember that the gain of the circuit, you actually never physically measure the complex part, right? You always just measure the magnitude of that complex number, right? Because in real life, you have real numbers, not complex, not imaginary numbers stuck inside, right? Because the complex part really just gives you kind of the phase, right? Right, so what we want to do is calculate the magnitude of this. And you guys remember how to calculate magnitude of a complex number? What should I multiply together and then square root? What should I write here? G, right, the complex conjugate, G star, okay? right? So now we get to deal with this. Let's just calculate what the square is first without doing the square root first, okay? Ooh. Okay, so, well, g I'm going to copy over. 1 minus omega square, omega LC square, plus j omega L. If I want the complex conjugate of a complex number, what do? Negate everything that has to do with the j's, right? Omega LC square. Right, there's also a j here, so that also turns out negative. Okay. I multiply the top numbers together, I get omega square, L square. Right, multiply these two numbers together, right? What was it? The thing is called FOIL or something like that. And these are like, what was it? Perfect squares of each other, right? Because you have something plus something and then something minus something, right? So basically, the result is going to be this part square and then this part square, right? With a negative sign, yeah. There's going to be r square 1 plus omega square omega LC square squared. Okay, that's the first term. The second term is going to be, well, it's minus j squared, but j squared is just minus 1, right? So you get a plus here, actually. Okay, and then you get omega square L square. Ugh. Okay. Okay, and then if you want, instead of g squared, you just want g, right? You square root both sides, right? Then you get that, right? You square root this, you square root this, you square root this, okay? That's what the gain of your RLC circuit is. Ugh. Lots and lots of stuff, okay? So we're going to look at this and just figure out, how does this function behave? In fact, I'll just show you what it looks like, right, down here, okay? If you plot the BOD plot of that gain function, right, you take the 10 log of that, multiply by 20, right, and you plot it as a function of the frequency divided by the resonant frequency, which is the characteristic frequency for an LC, right, whatever that is, okay, you get this, okay, right, you get this little mountain in the middle, okay. The dashed line is for different values, okay, but you still get the highest point in the middle, okay. Okay, and this is known as a notch circuit because it looks like a notch, right? Or what's also known as a band pass filter, okay? Because what's going to happen is that this is the band that's going to pass through the circuit for you to see the signal. This is how you pick out one particular frequency that you want, okay? So let's see how this why does this happen at exactly 1? Where by 1 I mean omega over omega LC. When this is 1, that means omega is basically omega LC, right? Whatever that number is 5,000, 10,000, 1, radians per second, right? The reason for that is that if you look up here, right, you look at this function. I think we had this sort of a little bit of this in homework 2 also. Look at this function, right? This number is the biggest, right, when the denominator is the smallest, right? Make sense? 1 over 0.00001 is a pretty big number, right? So, in order to make this number big, right, you basically want the stuff in the denominator to be close to 0, right? This term depends on just omega squared. This term depends on omega squared, so they kind of cancel each other out. But this part here, right, is 1 minus omega square over omega square LC square, right? If this number is exactly 1, this front term completely disappears, right? Does that make sense? If omega goes to omega LC, right, this whole term, the gain, right, just goes to omega square over omega square over 1. In fact, these cancel out. You get a gain of 1. And for a passive filter, that's the best gain you can get, okay? Your signal in, that one particular frequency that you want, you're not losing any of it, okay? Okay. And that's why on this plot here, right, when the gain is 1, the 10 base log of 1 is 0, multiply that by 20, you still get 0. So that's why here it's the one circuit that can actually theoretically get to 1. Sorry, get to 0 in the attenuation in this dot plot. Okay. All right. Just to kind of highlight some of the important variables that the book shows you how to use is that so the resonant frequency is of course going to be exactly where omega is going to be 1 over square root of LC, right? Omega RC is the same one as that decay constant that you already dealt with. Omega RL, right, is actually the resistance over the inductor's value, okay? And one of the interesting things is that all of these will have the right units, right? All of them, if you want to check the units in SI units, they're going to all have units of 1 over seconds, okay? All right. I think this one already did, right? Did they rearrange it in a better way? Let's see. Oh yeah, no, I have the same thing. Interesting. Yeah, okay, right. So the impedance of LC parallel to each other is this, okay? So next time you do homework, you can just plug that in, okay? As opposed to deriving it like what you just did, okay? The gain is this complicated function. I think it is the same. They might have, I think they moved some stuff around to make it look neater to type, okay? But this function and this function should be the same, okay? Oh yeah, there's a negative. Oh, I hate this. Negative 1/2 power. Yeah, okay. If you take the imaginary part divided by the real part of the gain, you will get this number, okay? I'm not going to do all the derivation of it, okay? What I want to do with the remaining 20 minutes or so is to cover something that the book doesn't cover, and I don't understand why this book doesn't cover it. And it's one of the thing, if you ever work on signal processing electronics, it's one of the most important things that people talk about. Okay, it's this idea called the Q factor. Okay, the Q factor, right? I think it stands for quality, but I think people just say, oh, just call it Q. Don't associate any word with it. Okay, the idea is that it's a measurement of how good your resonator is, how good your resonance is, okay? The way it does this is by basically quantifying how much energy is being stored inside your circuit divided by how much energy does it lose per cycle, or every period of your oscillation, how much energy does it lose? And hopefully that makes intuitive sense, you know, how much energy you're able to store divided by how much energy you lose per second, right? That tells you how good your device is, okay? Right? Because if you lose more energy than you store, that means it's going to slowly start draining out. But if you're able to store more energy than you dissipate, then you actually slowly build up more energy in your system, in your little circuit, and therefore you will get more and more energy as a bigger and bigger signal as time goes on, okay? So let's look at this for our little RLC parallel circuit, right? Let me just draw this on the right here. Right, remember this is the circuit we were dealing with. You have a little inductor, you have a little capacitor, and it all comes back. RLC, this is Vn, and you're taking this point as V out. Okay, so unfortunately I don't want to spend 15 minutes deriving each of these things, but if you go back to your general physics textbook, the amount of energy stored in a capacitor is equal to 1/2 the capacitance times the voltage across that capacitor square. Does this sound familiar at all? Something, okay. It's always going to be like 1/2 something square. Yeah. Okay. It's just kind of like kinetic energy that way. Okay. The amount of energy stored in an inductor, okay, and you want to write this down for sure, because you're going to need this for your homework. okay? Or you can just look it up in your general physics textbook. Is 1/2 L the current going through that inductor square. Yeah. All right, so that kind of gets us to the numerator here, but we have to figure out which one of these to pick, right? Should we be calculating the amount of energy in the inductor or the amount of energy in the capacitor? Okay, what do you guys think? Well, you do both, and the algebra gets a little complicated. You actually there's one that matters the most. Maybe if I talk through the denominator here, the power dissipated, right? In an idealized system, the only power that's being dissipated is through the resistor, right? The amount of power dissipated is the current going through that resistor times the voltage drop across that resistor. Okay? Another way to write this, right, is that, well, this can be the current square times R, or it could be the voltage square divided by R, right? That's a different way of just writing these things. Okay. So the amount of power being dissipated, right, happens at the resistor, right, proportional to the current square, and it could be written as being proportional to the voltage across that resistor square. Okay. Now if we think about our input, I don't know if I have enough space for this actually. Right. So let's make this Vn, right? So it starts off as a cosine, up and down, right? How is the output compared to this? If you're driving it at the resonance, what will be the amplitude? The same, right? Because the gain is 1. Is it going to be in phase or out of phase with each other? Right. So if omega goes to omega LC, right, this is basically going to be 0, right? Right. What's tangent of what gives you 0? sorry, it's not 0. There should be a divisor here. This gives you 1. I think there might be it's actually infinity. Okay, so sorry. Yeah, so I think there's just a missing slash there. Okay, anyway, so tangent of 90 degrees gives you infinity. Okay, basically you have a vertical line. Okay, so the phase between the input and output is offset by 90 degrees. Okay, so I'm going to try to draw this. Okay, so V out. So start off here at the maximum instead, right? Because this is 90 degrees. Okay, I'm going to draw the same as close to these cosine function as possible. Okay, right? So the voltage across this resistor, right, is biggest when V in and V out is the biggest, right? The difference between them, right? The most current, most power gets through this thing when V in is much bigger than V out, right? And where does this happen, right? If we're looking at this plot here, right? So V in is the red, V out is the green, right? It happens, right, at these peak values of Vn, right? That's when you get the most power being dissipated, okay? At these points, okay, the energy is actually all being stored in the capacitor, right? At these inflection point, that's when the energy is being stored in the inductor, and it transfers back and forth between these two devices, and that's why it resonates, right? So the energy is going from the capacitor and it's being transferred over to the inductor, and then it's being transferred back and oscillating back and forth. Hopefully this is kind of familiar from your general physics, right? Where you have a resonating oscillator, okay? So the energy we're interested in is when all the energy is in the capacitor, right? So that's why we want to pick this in this case, okay? In the homework, You're gonna do the same thing, but with these devices in series, okay? And I will let you figure out which energy you're supposed to use in order to calculate that, okay? Anyway, okay, so now we figure out that, okay, this is the energy that's when the resistor is dissipating most of its energy, okay? Okay, so the Q factor we actually want to calculate is going to be 1/2, well, there's actually a 2 pi in front, just to make things more fun, okay? The energy stored, right, which is in this little capacitor, okay? And this is where the voltage across that capacitor is the highest, right? This is the peak point in the capacitor, okay? Because we want this to be the highest. Okay, denominator, right? Okay, so this number here, remember these are RMS values, right? These are RMS values, right? How do you relate peak values to RMS values, right? So the peak value is bigger than the RMS value by a factor of 1 over square root of 2, right? So when we replace this, if we want to use the peak value here, it's actually 1/2 the peak value of that across that resistor squared divided by R, okay? So we plug this down here. Oops, let's not scribble down here, right? So we do the power dissipated here, which is 1/2 Vp squared over R, okay? Okay, this thing per cycle, it just means how much energy times time, right? So we want to multiply it by the period of our signal, right? Right? So these guys cancel out, these guys cancel out, right? And then 2 pi over t, do you guys know what that is? Omega, yeah. Everyone agrees it's omega? Yeah. Okay. And then we have C on top and then R on top also. So this is actually omega times RC. Okay. So that's the Q factor for a parallel RLC circuit. Okay. We can massage this even a little bit more, okay? Because if omega is approximately omega LC, okay? In other words, omega is going to be approximately 1 over square root of LC. We can actually plug that in here. So the Q factor for this parallel LC is 1 over square root of LC, and then we have R and C on top, right? And 1/2 a factor of C cancel out with the half of the factor on the bottom, right? So this is actually square root of C over L. Okay. Okay. And that's the Q factor that basically quantifies how much energy is being stored in your resonator divided by how much energy it loses every period. Okay. So obviously, the bigger the resistor, the better it is, right? And hopefully that makes sense, right? The resistor is basically constraining current from getting into the system, right? Or getting out, right? So the bigger the capacitor, the better, but then the bigger the inductor, the worse, okay? Right. So this is a completely theoretical calculation, right? Okay. And in lab 3, I think in lab 3, yeah, you can actually measure this in the lab, okay? Right? Once you built your circuit with a certain R, with a certain C, with a certain L, right? You can compute what this number is, right? There's another way, there's a way to measure it in real life in the lab, okay? Okay? You can experimentally measure this because the Q factor is also basically whatever the resonant frequency of that circuit is, right? Whatever omega LC divided by 2 pi, divided by what's known as the bandwidth of that circuit. It's like, what the hell am I talking about? Okay? And this is where the picture is more useful for describing this. Okay? So remember that for this RLC circuit, it always peaks at the resonant frequency, right? The highest point. So this is not a log plot. That's why it looks like this. It looks like kind of a Gaussian, right? On the log plot, it looks like a straight line. Okay, right? The bandwidth, right, is basically how far up from the resonant frequency you have to go in order to get to the minus 3 dB point of your resonator. Okay, okay, and then minus the the frequency you have to change in order to get to the left side of this. Okay, so this is just all about thinking about this picture. Okay, so just have this image in your head. Okay, don't try to calculate things yet. Right. So that means, right, this bandwidth is going from the low frequency to the, well, the high, basically the high frequency minus the low frequency, right? That gives you the width of this, you know, kind of Gaussian looking function, okay? Right? So you're going to be able to measure this in the lab because, right, you're going to tune, you built your little circuit, and what you're going to do is you're going to change the frequency from your function generator until you get the highest gain, right? Approximately 1, right? You're not going to get 1 because in real life you don't get 1. Okay? And then what you're going to do is you're going to change that. So once you measure this, you got this number up here, right? To get the bandwidth, right, you're going to change your frequency until you get to, remember what if the gain on top, at the peak is 1, what will be the gain at the negative 3 dB point? Do you guys remember what that number is? 707, right? It's technically 1 over square root of 2, but you know, 0.7 is probably close enough. Okay, so you're going to change your frequency until you get, you know, 0.7 of whatever your maximum gain is. If your maximum gain used to be 0.9, right? Take 0.9 times 0.7, right? Then you get that what that number is. Okay, and then you're going to roll it back to the other side to get the negative side, right? And then the difference between your high and your low gets you that bottom number, right? You compute this number, you should get a number that's pretty close to your theoretical value. And for the labs I've seen so far, if you get within a factor of 2, that's actually pretty good. Okay, the problem is that although all your inductor and your capacitor has resistance in it, right? They're not ideal. Okay. Okay, so you can actually get to measure this in the lab. Okay. All right. With the last, so any questions about these? About this Q factor thing, because this is not inside the textbook, unfortunately. I linked like a Wikipedia article about it. So if you just Google Q factor Wikipedia, you'll find this. Okay. I think the answer for this, actually the answer to your homework is also on Wikipedia, but you should derive it. Okay. Yeah. All right. So speaking of your homework, I just want to just kind of quickly describe what you get to do at home yourself, right? And so we did the parallel version in class. Guess what you're going to do at home? You're going to do the series version, okay? So RLC in series, you just basically take all the components and put them in series with each other, okay? So in this case, it's a little bit different, right? So all the current goes through every component, okay? And typically what you do is you take the output between the at the capacitor, okay? This is basically your V out, okay? You can take the V out over here also, but it'll be a little bit different. I think it's just offset by a phase shift 180 degrees. You're going to get an upside down signal instead, okay? And you know, the book tells you all the results. I don't think the book derives it, which is good, so that way you guys get to. Okay, it just gives you all the results. Okay, and you have a similar behavior where the magnitude of the gain, right? You still get this omega square over omega LC square. So when this is equal to 1, right, this whole term disappears, right? So you get the resonance when omega LC is at omega LC, right? Whatever that number is, right? If 1 over square root of LC is equal to, you know, 5,000 or something like that. If you drive that circuit at 5,000 hertz, you're going to get resonance. Okay. So I'll let you guys play around with that in the homework, okay? All right. One last thing just to kind of quickly chat about is that instead of building an LNC, let's say you don't have an inductor, right? What you can do is actually put a high pass filter and a low pass filter together in order to make a band pass filter also, right? Because what the idea is that, well, actually the picture is down here, right? Right? The high pass filter is going to allow high frequency signal to get through, right? So the blue is basically the first half, but then if you send that signal into a low pass filter, right, you will filter out the high pass also, and you end up with the stuff just in the middle. There is a price for this, right? Instead of getting a gain of 1, guess what this gain here is? Yeah, it's about half, okay? But if you don't have an inductor, that's what you get to deal with, right? I think there is an example in the textbook, but since I just want to, I'm out of time, so I'll leave that as an exercise for you guys to play with at home, okay? But the main thing is that if you want to build bandpass filter and you don't have an inductor, you can still do it with just capacitors, okay? And a lot of times if your signal, if the gain is not a big issue, and we're going to see that usually is not, because the next thing we're going to cover is semiconductor, and the one after that is going to be amplifiers. You can always amplify the signal, okay? And usually this is actually a more cost-effective way to make things rather than putting in an inductor, which A, costs more, and B, drains more power, okay? And that's what most people use actually instead of using inductors. All right. Hopefully this makes sense where you just kind of piggyback a high pass filter and a low pass filter together. You get both, but then you have to, you lose 70% each filter you use, right? Sorry, you lose 30%. You only retain 70% on each filter you use, right? And then when you do that twice, right, you only get half of the stuff back. Okay. Actually, this is actually an exact number, right? Because this number is actually 1 over square root of 2. Let me square it. Exactly 1/2. All right. Any questions before we wrap up today? I'm just going to hop out the recording.